Find a series solution to the given differential equation. Note that this is just y prime plus xy, so first order. That means there is only one solution, and we want to find that in terms of series. Okay, so for part A, the solution, and let y be a and x in. Okay, that's the solution. Now we want to find y prime, because the question has y prime, and from 0 through infinity, that will be power rule x to the n as n x n minus 1. Now this starts from n equals 1 through infinity. We can start from n equals 0, but that makes the very first term 0. Now with y and y prime, the ordinary differential equation becomes y prime is here, n a n x n minus 1 through infinity plus xy multiply this y by x, so xn times x is x raised to n plus 1. So a n x n plus 1 equals, right hand side is 1 plus x. Now we want to combine these two series. For this is n plus 1, this is n minus 1. Okay, so let's try to make xn, x raised to n in both. So n plus 1, so subtract 1, add 1. And here when I add 1, subtract 1. So this series now starts from 0 through infinity, n plus 1 a n plus 1 xn, plus this series now starts from 1 a n minus 1 xn equals, right hand side is already 1 plus x. Now we can combine these two series because xn, but this starts from 0, this starts from 1. We cannot go back, I mean that will be complicated, but we can go forward. So here is xn, so we made the same powers, xn. Now let's evaluate this for n equals 0, then the remaining sum will be from n equals 1, and we can combine. So for n equals 0, this becomes 0 plus 1, just 1, a1, x0, just a1, plus, now this sum starts from n equals 1. But look at the right hand side, we have a constant term and x raised to 1. So we want to make x raised to 1 separate, not inside this series. Then when we equate the coefficients, we can say this coefficient equals, here is 1. Okay, so I want to evaluate this for n equals 1 as well, so that x raised to 1, so we'll have a term containing x, and same thing here. So when n equals 1, 1 plus 1, 2, a2, x raised to 1, just x. Let's evaluate for n equals 1, a 1 minus 1, a0, x. Okay, why are we evaluating at n equals 1? Because we have x in the right hand side, and we want to get the terms containing x. Now this sum starts from n equals 2, and same thing here. So sum n from 2 to infinity, we can combine these two, n plus 1 a n plus 1 plus a n minus 1 and xn equals 1 plus x. Okay, these two are x, so we can combine these two, by the way, and this is constant. Now we are saying this left hand side is equal to right hand side. That implies this constant a1 should equal 1. And this constant, if we factor x out, this becomes 2a2 plus a naught, 2a2 plus a naught that's the coefficient of x, that should match with 1. There is nothing means 1, and there are no other terms means 0, so this coefficient should be 0. n plus 1 a n plus 1 plus a n minus 1, that should be 0 for all n bigger than equal to 2. Okay, that is, in fact, we've got a1 1. Let's solve this for bigger, so a2. So a2 will be move a naught over, so 1 minus a naught divided by 2. And in this case, solve for a n plus 1, that will be move this over, negative a n minus 1 over n plus 1. And this recurrence relation is true for n bigger than equal to 2. Okay, so the given question was just first order differential equation, so we have only one solution. That means there will be one constant, a naught. The very first constant, a naught, will be an arbitrary constant, so we can always take that to be 1. Okay, so let a naught be 1. Now we want to find all the constants, a naught, a1, a2, a3, a4, a5, etc. Okay, then a1 is what? A1 is found to be 1 as well, that we calculated. And how about a2? A2 is given by 1 minus a naught. A naught is 1, so 1 minus 1, 0 over 2, just 0. And now a3 is found, a3, a4, a5, etc. are found using this recurrence relation. So if we take n equals 2, we're going to get a3 equals negative a1 over 2 plus 1, 3. And a1 happens to be 1, so this is negative 1/3. Okay, how about a4? To get a4, we have to take n equals 3 in the recurrence relation. So 3 means 3 minus 1, 2, so minus a2 over 4, and a2 is, by the way, 0, so this is 0. In fact, this implies, look, what is the gap between a n minus 1 and n plus 1? That's 2. N minus 1, n plus 1, 2. That means a2 is 0, a4 is 0, a6 is 0, a8, a10, all are 0. Okay, and let's find a5. So we need to take n equals 4 in the recurrence relation, so minus a3 over 5, and a3 we found negative 1/3, so negative means positive, 1 over 5 times 3. We don't have to find a6, that will be 0, so a7, that's negative a5 over 7. A5 is found here, so this will be negative 1 over 7 times 5 times 3. Looks like we got the pattern. Starting a3, a naught, a1, we just keep both. A3 is negative 1/3. Maybe we can involve a1 as well. A1 is 1, a3 is negative 1/3, positive, negative. A5 is positive, negative, 3, 5, 3, in this case 7, 5, 3. So let's come up with the general term an. Okay, so thus an is equal to a1 is positive, a3 is negative, so negative 1 raised to n plus 1, and we are taking n equals, let's say, 1, 3, 5, 7. Those are odd numbers, so let's say this is not n, we can make it 2n plus 1, because n equals 2n minus 1, and we can start from n 1, 2, 3, etc. When n equals 1, we are getting 1. When n equals 2, we are getting a3. Okay, so that's n equals 1, so first a1 is positive, and we have 1 over, now on the bottom, what's going to happen? look, 7 7 5 3, so 2n minus 1, this will be 2n minus 1, and here to here 2 less, so 2n minus 3, 2n minus 5, all the way to 5 3, and we can always multiply by 1. On the top we have 1. Let's try to simplify this further. That's negative 1 to the n plus 1, and here if we want to write, look, 2n minus 1, 2n minus 2, 2n minus 3, 2n minus 4, so these middle terms are missing. If we multiply by top and bottom by 2n minus 2, 2n minus 4, all the way to 6 4 2, then this becomes a factorial of 2n minus 1, 2n minus 1 factorial. On the top 2n minus 2, because we need to multiply by that, 2n minus 2, 2n minus 4, all the way to 4 2. Okay, let's simplify further. That's negative 1 raised to n plus 1 over 2n minus 1 factorial. Now we can get 2 2 2 out from all these terms. 2 2 times 1, 2 times 2 will be 6, 2 times 3, 2 times n minus 2, 2 times n minus 1. So 2 factors. How many of them? 1 2 all the way to n minus 1. When we factor 2 out, n minus 1. So n minus 1 copies. 2 raised to n minus 1. Okay, and now this is a product of n minus 1, n minus 2, all the way to 2 1. So n minus 1 factorial. Okay, do not cancel anything, by the way. This is it, and this is n 1 2 3 etc. Okay, thus a solution is y equals, the very first term is a naught, then this we can write from n from 1 through infinity. In fact, this is n from 0 through infinity, but we could not include the very first, so a naught, n from 1 through infinity, an xn, and we have taken a naught to be 1 plus this sum n from 1 through infinity, and an, these n's are in fact 2n minus 1. Okay, so this is negative 1 to the n plus 1, 2 raised to n minus 1, n minus 1 factorial, all over 2n minus 1 factorial. This axn is ax raised to 2n minus 1. Okay, that's the final. Next, we need to go find the homogeneous solution of the differential equation. So homogeneous means right hand side 0. For the homogeneous equation, that would be then y prime plus axy equals 0. Now we can go through y equals a and x and series solution, but this is so simple, we can just separate the variables and solve for y. We solve, okay, we solve as follows: move xy over, divide by y, now integrate both sides. Y, this is the derivative of y, so natural log of y. I'm assuming y is positive solution. Integrate with respect to x, negative x is square over 2 plus constant. We are just finding a solution, so let's take that constant to be 0. Exponentiate both sides. E raised to ln y is just y equals e raised to negative x is square over 2. Okay, done.